Imagine looking up at a skyscraper, watching a thin steel arm swing a load weighing 30 elephants. You're standing directly underneath, trusting this titan won't buckle and crush you. But here's what nobody tells you. These cranes operate on a razor's edge. A single microscopic pocket of trapped gas in the steel can cause the entire tower to snap instantly. A mega crane must survive hurricane-force winds while bolted to a concrete pad no wider than a living room. If the metal bends by even a fraction of a degree, leverage turns catastrophic, creating a deadly pendulum. Traditional steel would simply fatigue and tear apart under these massive dynamic forces. Conquering gravity required engineers to completely rewrite the laws of metallurgy. Our journey begins in the massive iron mines of Brazil and Minnesota. To give the crane its legendary strength without adding dead weight, raw iron is alloyed with rare niobium and vanadium. These exotic metals cost up to $40,000 per ton, but they are absolutely essential. The mixture is smelted at 1600 degrees Celsius, purifying the iron to 99.5%. Full microphone hash narration. But steel is only part of the story. The hydraulic system relies on precision-machined cylinders, pumps, valves, and hoses manufactured from specialized metals and synthetic materials. Rubber components often begin with natural rubber harvested in Southeast Asia and synthetic compounds produced in advanced chemical plants. Thousands of individual parts must travel across continents before they ever reach the factory floor. Think about this. A finished amphibious excavator may weigh more than 30 tons, yet its flotation system must distribute that weight carefully enough to travel across terrain that would swallow ordinary construction equipment. That requirement forces manufacturers to use huge quantities of precisely engineered steel while controlling every gram of unnecessary mass. It's a balancing act that begins long before the first weld ever appears. Of course, extracting and processing these raw materials comes with a cost. Mining operations consume enormous amounts of energy, while steel production remains one of the world's largest industrial sources of carbon emissions. Manufacturers now invest heavily in recycled steel, cleaner energy sources, and more efficient production methods. Yet even with these improvements, creating the raw materials for a single amphibious excavator remains a remarkable industrial undertaking. The moment the raw materials enter the factory, the pace changes completely. Huge steel plates weighing several tons move across the production floor on overhead cranes. Computer-controlled plasma cutters begin carving precise shapes that will eventually become the excavator's floating pontoons. Temperatures inside the cutting zone can exceed 20,000 degrees Celsius, or more than 36,000 degrees Fahrenheit, while cutting heads move at speeds approaching several meters per minute. The sound is a constant roar of electricity, hot metal, and flying sparks. Next comes bending and forming. Massive hydraulic press brakes apply hundreds of tons of force to shape thick steel plates into the curved structures needed for flotation pontoons. Some sections require multiple forming cycles lasting several minutes each. You can hear the deep groan of machinery as steel slowly changes shape. What looks effortless from a distance actually demands extraordinary precision because even a few millimeters of error can affect buoyancy. 9 Microphone hash narration. The formed sections now move to welding stations where the real structure begins to emerge. Robotic welding systems and highly skilled welders join hundreds of individual steel components together. Welding arcs reach temperatures near 6,500 degrees Celsius, or almost 11,700 degrees Fahrenheit. The air fills with the smell of heated metal, while blue-white flashes illuminate the factory like lightning storms. A single pontoon can require dozens of hours of continuous welding. The final step is a brutal pull test where winches are subjected to 125% of their maximum capacity under 500 bar of pressure. The entire rig groans under the strain, emitting a low, terrifying hum as cables vibrate. If the components survive this 30-minute torture test without a single microfracture, they are cleared for global deployment. Once welding is complete, technicians inspect every critical seam using ultrasonic and magnetic particle testing. Sound waves travel through the steel searching for hidden defects invisible to the human eye. Even tiny cracks can trigger repairs before production continues. Most people never see this stage, Yet it determines whether the machine survives years in some of the harshest environments on Earth. Assembly begins when the completed pontoons meet the excavator body. Heavy-duty cranes carefully lower components weighing several tons into position. Workers guide the structures with incredible accuracy while hydraulic systems, engines, fuel tanks, and electrical networks come together piece by piece. The machine suddenly starts looking alive. What was once a collection of parts now resembles the amphibious giant it was designed to become. Meanwhile, another part of the factory builds the excavator's hydraulic heart. CNC machining centers cut steel components with tolerances measured in fractions of a millimeter. Rotating tools spin at thousands of RPM while coolant sprays across glowing metal surfaces. The machines never seem to stop. Day and night, they transform raw metal into precision cylinders, valves, and pump housings that control every movement of the finished excavator. Then comes one of the most fascinating stages of the entire process. Technicians install specialized amphibious track systems designed to operate in both water and mud. Every track section must move smoothly while distributing weight across a large surface area. The completed system allows the excavator to travel across terrain that would trap conventional machines within seconds. What happens next surprised even experienced engineers.